Hi, my name is Jerry Thomas. I'm from the Milwaukee School of Engineering, and today my talk will be about strategic ownership and using simple games, non-zero sum and zero sum games to elucidate that in the decision process theory. My name is Jerry Thomas, and I'm going to talk today about some ideas, if I can make this thing work, of using game theory, and in particular a decision process theory, to investigate some ideas that are pretty simple that we all take for granted. And one of them is about decisions, like who owns a decision. When we make a decision, we usually think we own it, right? So when I drive from Chicago down to Champaign, I have some choices, right? I can take a couple of highways. I can go down the toll road or not the toll road. I can take a plane, I can take a train. But my decisions, in fact, are limited. And they're limited by choices that are outside of my control. They're constraints. Somebody actually had to build the roads, build the airplanes, build the trains, build the tracks. And those choices were made a long time ago outside of my control. So if I have a theory of how we make decisions, in that theory I had to take into account those constraints. We do that all the time in physical theories. When I talk about standing on the podium, for example, it's static, but I don't take into account the fact that it's actually not really static. It's made up of atoms, and the atoms are moving up and down, and I'm probably moving up and down a little bit, despite nerves, right? Independent of that, I'm moving. So how do we do that? That would be an entire course. I'm going to use the ideas that come out of game theory and out of decision process theory to talk about how we might deal with those in a simple way. So first, so my background is in physics, and the way I go about understanding things is I pick toy models. And I'm going to pick a very simple toy model of a game called rock, scissors, papers. Everybody know what that game is, right? Rocks, papers, you know that game. It's a simple game, but I'm going to use it to try to uncover or elucidate the idea behind making decisions. So the first thing I'm going to do with rock, scissors, papers is we know that as a game where everybody plays the game the same way, right? But what if I change the nature of the game a little bit? I could do that. I can make rocks a little bit more exciting for each player. So I'm going to do that, and that makes the game no longer a zero-sum game, but a non-zero-sum game. So that's kind of an interesting thing. And part of what I will do in talking about that game is talk about something from game theory, which is called Nash equilibrium, which is this very, anybody know what Nash equilibrium is? Yeah. It's some idea about a max-min solution to linear programming that comes out of game theory that says people tend to do what's best for them, having considered all the worst things that could happen to them. So I think I said it right. So that's kind of standard for a static game. We're going to find that that is not an appropriate definition of stationary behavior when you have dynamics. And I think people that study dynamics would understand that, see that right away. So game theory concepts, since somebody knows Nash equilibrium, you probably know as much as anybody here about game theory. But the key idea of game theory is, for me, there are certain strategies that we can choose. And we can turn a game of I do this, you do that, I do this, you do that, boil it down to a single strategy of what was my choice, what's his choice, we make the choice once, that's the game. Decision process theory, on the other hand, says those set of choices are like a space, and in that space it's a point, and those points can move over time. So as opposed to static, we can now have things that move. So if we incorporate that, the only thing that we are missing then is how do we incorporate constraints? And we do that in the theory. The theory does that in a very nice way. just like it's done in physics, that you treat constraints as stresses that are outside the theory, but you can specify, if you like, their energy and momentum. You make sure that you treat some properties correctly, which allows you to do kind of like a least action or least path for the whole game. Let's see. So for a zero-sum game or a non-zero-sum game in a geometry, one of the key aspects of a geometry is it may work in a space that's more than one dimensions. Okay? And in the space, in game theory, typically you think of a game as a game matrix, and it has some values. But the game matrix will be multiplied by a number, like a charge. And if you take the analogy of a charge a little bit further, if you had a charge between two plates, it could produce a field. And the field that it would produce might be the game matrix. So if it's a constant field, that would be just like a capacitor. That's the idea. And the distinction between a zero-sum and a non-zero-sum game would be which way are the fields going. Okay? For a zero-sum game, they would go in the same direction. For non-zero-sum game, they would go in the opposite direction. So that would be our key. And this is moving a little bit faster. So I'm going to not do a lot of this notebook, by the way, was set up to be used by students. So it has an initialization set, which I'm not going to do. And the students can then just go to a list of possible games or add their own games. And so they can go and they can look up, oh, I want to do a rock, scissors, paper game. They can go find a rock, scissors, paper game. And they would set up a game matrix, okay? So the 0, 2, minus 1, just I kind of compressed it. I did a new matrix form to make it into a nice matrix. But the 2 that you see there would be a 1 in a normal game. That's the piece that I added that makes it a non-zero-sum game. And then if you play rock, scissors, paper, right, what are the choices you normally make? A third, a third, a third, right? You play each one equally, right? So if I change the nature of the game by adding the 2, well, I don't play them equally anymore. But each player sees a different value to what is unequal. So if they both did it, I could try to make a composite game out of that. And this is what I would get. The composite game would behave actually very differently from what I would have expected. What would I have expected? The first thing I expected when I did it for the students is it would just oscillate around some value. Okay? I would believe, yeah, the values are going to be a little different. What I didn't expect is I get this exponential behavior. What's the exponential behavior coming from? Underlying the theory, there is a game matrix which looks like an electromagnetic field, which has both a time and a space component. The space components give you really payoffs, which are just like a magnetic field, but that's the game matrix. The time components give you an electric field, which is really the valuation, the game values of what happens when you play the game. The eigenvalues of such a thing can be both real and imaginary. If I just had the magnetic field, it would be purely oscillating around the magnetic field. The other parts are because I can have things which are growing exponentially. That's okay. Time grows exponentially too. The relative rates are still great. There's nothing wrong with that. It's just I didn't expect it. Is that the actual behavior, however, that we would expect? My argument is no. My argument is, if I can, what we looked at just now, although the space is fairly complicated, I mean, it's like a 9-dimensional space or something. 3 and 3 are 6, which is 6. Time is 7, but each one has their own internal strategy, 2 more, that's 9. In a 9-dimensional space, how do I track that? Well, if you're familiar with tracking phenomena for fluid flow, for example, as opposed to tracking everything, you track a stream. And then for each direction in space, you track how the stream behaves. That's the velocity of the stream. If there are 2 players, what's new is they each see a different world, they each have a different boundary condition, so they each have their own version of a stream. So the 2 directions I should choose would be stream of player 1, stream of player 2. Now, instead of getting differential equations to solve for the streams, I get partial differential equations, because they're coupled now because I have 2 streams to consider. So I have to consider a mesh. And unfortunately, I did this before version 12. So I had to iterate my partial differential equations are nonlinear, so I had to iterate them, which was a pain in the neck. So I had to specify how many times I was going to iterate them, keep a little progress bar. The iterations took a long time, so that's why I'm not doing it for you in real time. But that's the iteration. So I'm not going to do that. But once I've iterated the solution, my behaviors along the diagonal, when the 2 streams are equal, for the owner streams are equal, is no longer what we saw before. It's quite different. And this is, I claim, not just an artifact of this toy game, but it's a real fact when you start thinking about it of how any game must work. Any game can have Nash equilibrium values on the boundaries where each player thinks they own what's going on, but they own it this boundary, this guy owns it on that boundary. What goes up the middle, they don't own. But the equations own it. The equations can understand how to interpolate from the boundaries to the middle, and this is the behavior you get. You can look in a lot more detail. I might come back and talk about what is market capital, but here would be the flows of one flow versus the other flow. We just saw along the diagonal. This is now a lot more general, looking at the 2 flows. If I solve the equations exactly, I would have a 9-dimensional set of partial differential equations. I could really track things. But just like streamlines are very useful, these ownership flows are very useful for getting an idea. They already show that potentially those flows could turn in on themselves. And I've run solutions where they actually do. So you can get vortices out of this. You just have to turn up the values of what's going on. So you can look in more detail for each of the strategies individually as opposed to a single curve. You can look at each curve, for example. This would be player, so I have blue and red. Blue is player 1, red is player 2. Blue and red comes from IBM when people in the Cold War, right? Red were the bad guys, blue were the us guys, right? So I picked the same model. So this is red, which is player 2, choosing rock. You can see it's not like along the boundary, you can see it's pretty constant, but you can see what the equations do in terms of boosting things up, and it's a little asymmetric. And you would expect scissors and paper, they will have some behavior which would be interesting to sit down and think about, but for time I won't go through all of that. And then blue, it's asymmetric on the other side. And for rock, and then you can go through and look at and of course time is a variable too, so it has a behavior. Now time in this sense is like physical time, and as you go along a path, then you have a propagation time. So you take all of that into account. So that's what you get. And what we did depend upon really focused on the constraints. So here's what went in it. I said the decisions are like creating paths along the highway. These constraints they're constraints, okay? And they're set by assessing stresses that say, here's what each player sees. Now, each player ideally sees stresses. If you thought about it as a fluid, the stresses would be, from each player's perspective, sort of isotropic. They wouldn't, the things that they think they own, they would say, yeah, they're all the same to me. And the other player would have the same thing. Now, in the world in which they play, those stresses might not look quite so isotropic. So I can actually look at what that, take the different strategies, create an ellipsoid of the stresses, and see how isotropic or not is it. Well, that looks pretty isotropic if you look at the equations of the ellipse. The error, it's not an error, but the anisotropy, I can't say that word. Anyhow, the non-isotropic nature is very small. The flows, each player has an internal strategy which nobody cares about, which was what I call their internal flow. Their internal flow, since nobody cares about it, is effectively a symmetry of the theory, and so it acts like a charge. It turns out in differential geometries, that's always true. Whenever there's a charge, there will always be an electric and a magnetic field associated with it. And if there are 2 players, there will be 2 such fields. If there are 10 players, there will be 10 such fields. Sounds like really weird. If you're in particle theory, it's not really weird at all. It just says when you have unified theories, you have lots of these fields. And in this case, the fields are very simple. They're sort of U1 fields there, and they all commute with each other. So each player has a charge or flow that they see along their boundary. It has a behavior between these 2 plates that goes from one to the other, and therefore it has a shape, and then the shape gets propagated from the theory just as well as all the other flows. In this case, those flows are very simple. Let's see. So we did this for rock, scissors, paper. There's another game we could do, which is how many people know how to play tic-tac-toe, right? We all know how to play tic-tac-toe. But how many people know what the strategy is to win or to make sure you don't lose? You all know there is one, right? But can you articulate it? You don't remember it, right? So, but it's a game, right? And it's an interesting game because, first of all, to articulate what those strategies are illustrates a very fundamental issue in game theory, which is how I distinguish between playing the game of tic-tac-toe and isolating or characterizing what those strategies are. Where do I find the answer for the tic-tac-toe? I go to Wolfram, as a matter of fact. It's all there. I just go to Wolfram Alpha and say, tell me all about tic-tac-toe. And it tells me there are 9 strategies, 9 pure strategies that I can make, which is specified by the 9 boxes of tic-tac-toe. But what I do for each of those boxes is not symmetric between the 2 players. X is player 1, O is player 2. So I won't go through the details again, but needless to say that there's a decision tree matrix that's associated with making each of these boxes. And of that decision tree, it turns out it doesn't really matter. X's choice doesn't have to be all 9. X either chooses the middle box, a corner box, or an edge. And it doesn't matter which corner or edge it picks, it's all symmetric. But then I have to keep track of all the 9 choices for the other guy. So if I do that, and I work out the game matrix for that, I get Nash equilibrium. And Now, the difference, however, is if I just do the Nash equilibrium, I'm going to get, since it's a zero-sum game, nothing exciting happens. But in systems where nothing exciting happens, what do? I take a hammer and I hit it, called a disruptive force. Okay? So the standard way to understand a system is hit it with a force and then see what happens. So I have a disruptive flow there, and I hit it, and I see things, some of the choices oscillate, and some of the choices are like pretty good. O1, by the way, is if you're a player O, your best strategy is always hit the middle. And you can see that that's like, but the other strategies, if you do sometimes one of the other strategies, it generates little oscillations for X and so on. So the game is played over and over again. Treat this now as ownership game. Now, again, 2 dimensions. Again, iterate it. This version of my iterations was not as successful because my mesh was really not very good. That's where I'm hoping that the new ND solve is really going to help me out. By the way, when I did it a quite different way, these curves are really nice and smooth because I can choose really nice meshes. And it has the same characteristics here, but I'm going to do it the same, use the same model. And let's see. Focus on here. Again, there's a neutral behavior which is different from the Nash equilibrium. The Nash equilibrium in this case would be just to choose one of the stationary pieces, no excitement, and I could have done that, and I would have gotten for this stationary. But if I choose a disruptive flow, which is dynamic, I hit the system, the neutral behavior is different. And you start to see a lot more turbulent behavior because, why? Because I hit the system. So again, I can look in detail at player, the best choice, nothing exciting. Lots of structure, though, on the sort of the non-ideal choices. One of my students, by the way, used this type of model to look at some gaming situations and saw really sort of the same thing, that people who play games on the internet, they know that there's certain optimal choices, and if they play it, everybody knows their optimal choices. Other people then will disrupt the system and play non-optimal choices, and it causes little oscillations in the overall system. And they're stable. They keep going back and forth. And these are stationary oscillations, not behaviors that will somehow go away or transient. It's a distinction if you think of an analogy between electromagnetic theory. There's DC currents and AC currents, which are both stationary, both different from looking at transient behaviors. These are not transients. These are pure stationary behaviors. So lots of things that we can do with that. Conclusions. My takeaway is that the strategic ownership is a key thing in decision making. It's one that's ignored because it's invisible mostly, because we normally don't, we just assume that there are choices. We forget the fact that there are roads that determine our choices. Because of that, what we should focus on will not be things, traditional game theory things like Nash equilibrium, but we will have to consider what are the neutral behaviors. And it's the amalgam of the processes of the equations, okay, some kind of geodesic or least shortest distance between two paths, and setting up the boundary conditions. So the ownership reflects both those two options. Another aspect, which I didn't have time to talk about, is in addition to, he says stop, but I'm going to go one more minute. There are additional things in the theory that you have to pay attention to, which also have boundary conditions. So with that, I will take questions.